Here, I will be discussing a bunch of different properties of organic compounds that, upon thinking about them, I can't just think of something or some term that generalizes all of them, but I notice that all of the things I will discuss here are things that you can observe the moment that you look at the structure. So, though it's ambiguous, I'm going to call this discussion as structural effects. And these structural effects are things that can influence a lot of things. Primarily for our discussion here, two things: stability and acidity. Now, some of the stability related discussions are gonna be cut because I'm gonna reserve them for when we discuss isomers, especially conformers. But for now, let's get straight to it. First, in some structures, you can already notice things called strains. And generally, when you call a structural effect a strain, this is something that kind of forces bonds away from the expected bond angles, the expected angles. And meaning it's basically like how we use the word strain in real life. Like when something is strained, it's kind of stretched beyond its normal capacity. And we know that's not a good thing. That's why, in terms of stability, strains are actually things that reduce the stability of a compound. In very vague terms, we can just say that it's not good. Okay, and let's try to make it more concrete. When we say it's not good or it's not stable, that actually means that it has a lot of energy. And in chemical terms, in kinetic terms, usually we do note that compounds which are unstable are the ones that tend to have a lot of energy in them. So I think we're having some basis from the words for the words we're using anyway. So let's go to the first type of strain. We have angle or ring strains, and these are deviations from the original bond angles. Normally, when we talk about rings or cycloalkanes, we follow sp3 hybridization, and the angle for that is 109.5 degrees. And experimental data, we can't argue with experimental data. Experimental data show that cyclohexane has zero angle strain. It's like, hey, this is the gold standard of rings. If you're not cyclohexane, you're not the most stable one. And the idea is the more I deviate from it, meaning the more carbons I add or the fewer carbons I have from cyclohexane, the strain increases. Like if instead of 6 carbons, I have 7, or let's say I have 8, and so on, my strain actually increases. So I can say that comparing cyclohexane from, let's say, cycloheptane, which is this one, I can say that cycloheptane is less stable because it's going away from the cyclohexane. Or for example, if I have cyclopentane or cyclobutane or cyclopropane, the strain even goes higher the moment I go away from this point. So like if you are being asked, okay, which is more unstable between cyclobutane and cyclopentane? The mere fact that cyclobutane is farther away from cyclohexane means that this one is probably more unstable or less stable than cyclopentane. And here, I'm not actually going to compare because here the reality is the stability decreases from this to this, which is equal to this, then this, and this. Because in those cases, we actually need to look at values. But for the purpose of simplicity, we're not going to do that. Just the idea that the more you go away from the cyclohexane, the more unstable your ring becomes. Okay? So that's angle strain in the simplest possible explanation. Next, we have steric hindrance. It kind of is related to the stereos word, which actually means space. And because here in steric hindrance, this is due to the presence of bulky groups. Though I have to clarify, sometimes you may not have bulky groups, but if the atoms are so close to each other, it's also as if they are competing for space, the stereo or the steric effect or steric hindrance. Like for example, if I have here two benzenes with two methyls each, And maybe if you've already practiced your nomenclature, we know that this arrangement of methyl groups is called the meta, and then this one is the ortho. The fact that in my meta, my carbons are a little farther away, and in the ortho, the carbons are kind of closer. You can just imagine that there is tension building up in this area. So that's bad because tension means instability. It means a lot of energy. So that means that this is actually the one with the more steric effect, and this is the one which is lower in terms of stability because steric effect is a strain, right? Just like angle strain or ring strain, steric effect will also lower the stability of a compound. Now, we also have something like this. We will discuss this more when we go to isomers between the both version of cyclohexane or the both conformer and the chair conformer of cyclohexane. If we focus or like cherry pick on two particular hydrogens, particularly the hydrogens here for the both, and for the chair, um, we can convert that into these two hydrogens. Comparing the distance of these two hydrogens in the chair versus this in the boat, we can clearly see that the hydrogens in the boat are so closer to each other. So therefore, this is higher steric effect, and therefore this is less stable. And the chair conformation is more, uh, what did they write? More stable. It's because of the differences in steric effect. Okay, and we will see more of the steric effect when we go to our other topics. Another strain that exists is torsional strain. It's a steric effect that results from rotation of single bonds. Okay, and really focus on the word single bond because, as we will know later, double bonds don't really have the capability to rotate. In fact, I already mentioned that in our discussion on hybridization. The fact that the moment I have a pi bond or a double bond, rotation is not possible anymore. So let's say I have this compound right here. And of course, we know this is called ethane. It has two carbons, only a single bond between the two carbons. And the only way that we can look at torsional strain for ethane is if we look at it at a different perspective. So imagine that you get this molecule and then you put your eyes on front of this perspective. It's as if you're looking at the white carbon on front, and then this white carbon is blocking the yellow carbon at the back because, of course, it's at the back. It's being covered. So we can imagine it looking like this. So let's say that the circle here that is white is the carbon on front. And you can just imagine that behind this one, I have the carbon that's color yellow. But I'm not gonna write that anymore because again, it's as if the white carbon is overlapping the yellow one at the back. And you know that the yellow one has three H's. Okay? So we can write it like this. By the way, the way we write this, like looking it from the front, is called the Newman projection. In some textbooks, they have another projection, the Sawhorse one, but the Newman projection is more popular, so we're gonna stick with that here. And the torsional strain is basically the measurement of how much our angles overlap. When you say dihedral angle, it's the angle between a bond in the front and a bond at the back. Let me show you what I mean. Let's say this is a bond at the front. Sorry, this is a bond at the back. I stand corrected. This is yellow, right? And this is a bond at the front, which is color white. And if you measure the angle between the bond at the front and the back, that's a dihedral angle. And the idea is the greater the dihedral angle, the better, because when I have a larger angle, that means that these two hydrogens are farther from one another. For example, in this version, which we will repeat later in isomers called the staggered conformation, all my hydrogens are so far from one another, and their dihedral angles are big like this. And therefore, there is low torsional strain here. Unlike this one, which we call the eclipse, called like that because it's as if the hydrogens at the front are eclipsing or overlapping or covering or whatever word you want to use. They are overlapping the hydrogens at the back. The fact that they are so close to each other, they are on top of one another, they're so close. And we don't like things that are close, right? So, in that case, this is actually higher in terms of torsional strain. In short, this is less stable. In fact, this is something that I will not really discuss completely right now, But when we discuss conformational isomers, specifically those that have something to do with torsional strain and rotation, we will know that there are a lot more than just staggered in eclipse. But this is for a future discussion. For now, one more set of structural effects I will discuss is called resonance or delocalization. So here, it's kind of more challenging because you have a lot of requirements to look upon. So first, when we say delocalization, this means that I have my electrons that are constantly moving. They are constantly moving. And of course, it's kind of difficult to teach something that's constantly moving in this setup. I would have preferred like some kind of GIF or animation, but we don't have something like that. So we're gonna have to do shortcuts in this case. Okay. So first, um, the requirement for you to have a delocalization is you must have electrons of your choice. Like if it's sigma delocalization, my electron source is a sigma bond. If it's pi resonance, my source is a pi bond. If lone pair resonance, my source is a lone pair. And they should be beside, as in literally beside an sp2 atom or an sp2 carbon, such that we can imagine the electron moving from where it was originally placed to where we have the double bond. And I will try my best to show you what that means, but I do admit it's difficult. But let's try this one first. If you have sigma delocalization, which we often call as hyperconjugation, you must have first an sp3 carbon. That is because the sp3 carbon has the highest proportion of sigma bonds. Okay, and uh, and the fact that I have three H's, I could use any of those three sigma bonds to H for this to happen. And notice that I have here my sp3 carbon literally beside this carbon, which the fact that it has a double bond is sp2. And so how can I show you that the electrons are moving? It's as if what we're doing is this bond, let's say, moves to this area. And then as a consequence, the carbon here must move one of its bonds to this other carbon, because if I don't, my carbon at the middle would have 5 bonds. If you don't believe that, you can check it out, pause it, and then see for yourself. But long story short, what will happen after this is we can imagine, like, let me try to show you step by step. So let me copy everything first. And then I told you guys that this bond here from hydrogen, right, is going to be gone because that bond will move here. So it will move here. And as a consequence, the double bond here will have to move at the carbon at the rightmost part. When that happens, my carbon here is a negative charge. Oh, by the way, since hydrogen here is left behind without electrons, it will become positive. And guess what? It can actually go back, getting us back to this structure. It's like back and forth, but actually that's not true. But I will clarify later why. But first, let's move to pi resonance. So pi resonance involves movement of pi electrons. So for example, this is the pi bond that we want to move. We can imagine it going here, and then the carbon here will have to give its double bond to the other carbon in order to uh, have our consistent bonding. So if I do what I showed here with the arrows, this bond right here will move to the center like so, and this bond here will move to the rightmost carbon like so. And remember that the carbon on the left has lost its double bond, so it becomes positive. And guess what? Just like what I said a while ago, the electrons can go back to original. It's like going back and forth, back and forth. And then lone pair resonance means I should have a lone pair, usually from a nitrogen, and my sp2 carbon is here. So just like what we see in the first two examples, my lone pair moves to the next bond, and then as a consequence, the double bond here will move to this carbon. If I do that, what will happen is my nitrogen will have a double bond with the carbon at the middle now, and if my double bond moves to the carbon at the right, then my CH2 at the rightmost spot would be negative. Oh, and by the way, the fact that my nitrogen has given up one of its electron pairs, it will become negative. And just like a while ago, the electrons can go back here, getting us to the original state. So hopefully you see this back and forth. You can kind of imagine the electrons moving back and forth, but let me clarify that in reality that's not the case. It's not actually going back and forth. It's actually the electrons moving constantly, being dispersed uniformly throughout all those atoms. But it looks ugly if we try to draw that. So this is something that we see more in introductory textbooks. A perfect example of resonance is benzene, right? Because if I have benzene, I can have my pi electrons here moving here, which is followed by this moving here, then this moving here. That means that my double bonds have just rotated like that. And in reality, it's not really this which is correct or which is this is correct. The reality is you should imagine benzene where all of its pi electrons are circling, swirling, constantly inside, just like this. In fact, this is the most accurate way of writing benzene. But because in organic chemistry, we cannot count the electrons using this circle, we kind of prefer this one as the more formal structure. Right. And what you should do is is to remember that resonance is a stabilizing force. Anything with delocalization is more stable than anything without. Okay. It's a separate challenge for us to identify what delocalizations exist. But let me share to you shortcuts. So the shortcut for hyperconjugation is the fact that I have an sp3 carbon directly attached to an sp2 carbon. Just like this one, sp3, and then this is sp2. For pi resonance, all we need is a conjugated system. Remember, conjugated means double, single, double, alternating single and double bonds. That's the case here, right? Double, single, double. Okay. Benzene is also an example of pi resonance, right? Double, single, double, single, double, single. And for lone pair resonance, I usually need an oxygen or an oxygen, a nitrogen or an oxygen that is directly bonded to a carbon, single bond. Like this one, I have a nitrogen, single bonded directly to a carbon. That is, don't forget, sp2. Because if it's not sp2, we won't have any delocalization. Okay. I actually forgot to put practice items. If you guys wanna have some practice items, I can upload something soon. But for now, let me proceed to the next type of structural effect, and this is called the inductive effect. So actually, the inductive effect is the overall push or pull of electrons. And here, we're gonna be revisiting the idea of electronegativity. We should recall that electronegative atoms pull electrons, and electropositive atoms, or ones which are not electronegative, are more likely to push electrons away. So for example, I have this structure at the uh, middle, and let's try to analyze what things here can be electron withdrawing or electron donating. And usually if that is the case, we have to put it into context. We always need to ask the question, electron something where? So we need to indicate, for example, just to be clear, let's try to focus on this carbon, for example. Okay? What are the things around it that will push or pull electrons away? Push to it or pull it away. So first, this one, for example, if I have COOH, the fact that I have oxygens in COOH means that I have electronegative stuff right here. And electronegative means pull, right? And therefore, if COOH pulling electrons, we call the inductive effect electron withdrawing. Because, well, practically speaking, withdrawing and pulling are like almost synonymous. Okay, not of course exactly the same, but they kind of are similar in terms of meaning. For example, chlorine here is also, guess what, electronegative. And the fact that it's electronegative, it will pull electrons. We can also say that chlorine here is electron withdrawing. Okay. Whereas, if I have a CH3 here, a carbon is not usually hungry for electrons. Uh, That should be one thing you should have noticed in our previous discussions. And the fact that it is more of pushing electrons instead of pulling, we can call carbons or methyl groups or alkyl groups as electron donating groups. It's as if you can imagine. I did mention overall push or pull, right? So in terms of this carbon, what's the overall push and pull? Well, these two withdrawing groups pull the electrons away from the carbon at the middle, yet this CH3 at the bottom gives electrons to it. So that's the overall kind of push and pull of electrons. Okay? And you should know shortcuts. Like the moment you have like electronegative atoms like chlorine, bromine, OH, sulfur, things like that, usually they are withdrawing. But donating groups are most often than not R groups, alkyl groups, or methyl groups, and whatnot. Okay? So now, let's try to just very, very quickly apply the idea of structural effects to our acidity. So, one thing that we should recall here is the fact that acidity, as defined according to Bronsted and Lowry, is the capability to donate protons or H plus. For example, I can say that carboxylic acids are acidic because, long story short, they have the capacity to release these hydrogens. And maybe sometime soon, if I make advanced organic chemistry discussions, I can show you step by step with arrows how this COOH becomes its conjugate base COO minus. But that's not the point here. Let's just answer something more simple. Like, if I have these three structures, what of the three is most acidic? What is least acidic? And what is in the middle? Let's try to apply the principles that I wrote here. I mentioned that if I have electron withdrawal, it increases acidity, and electron donation will decrease the acidity. The idea here is that as my electrons go away from H, then it becomes more acidic. Or if my electrons go towards this H, it goes more acidic. You can try to pause this one and repeat what I just said. And if you think about it, electron withdrawal is kind of appropriate to what I said, that we pull away from H. Or donation means we give towards H in terms of electrons. So for example, here I see bromine. And I know that bromine is an example of a withdrawing group. And because electron withdrawing groups increase the acidity versus these two compounds that don't even have a bromine, then we can say that this is the top one in terms of acidity. This is the most acidic. Now, it's a battle between this one and this one. So what's the difference? Clearly, you can see that at the rightmost part, I have here an extra methyl that is not present in the leftmost structure. And since a methyl group is a donating group is supposed to decrease the acidity. So meaning, this one has none of that, this one has that, and this decreases acidity. So between the two, this would have the lower acidity. So this is the last, and this ends up at the middle. So that is how you very crudely apply the type of inductive effect to acidity. Now let's go to this one last example below. Same thing, give number 1 to the most acidic, number 3 to the least acidic. So let's try to analyze this first. Notice that all of them have OH, and that is because the OH here is the most likely group to release the H and become acidic. Now, notice that two of my examples have benzene. And remember that benzene exhibits what we call, right, resonance. And we know that resonance or delocalization increases acidity. In other words, I'm trying to say here that comparing these things with benzene versus this one which does not have benzene, then I am confident that these two are more acidic. And comparing these two to this, since these have delocalization, they are more acidic. So this is definitely the least acidic example, so this is 3. So now the question is, let me just erase this because there's too much of a mess here. So comparing the two here, which is more acidic? What's the difference anyway? Here, I have plain benzene. But here, I have an extra carbon. What does carbon do to the to the acidity? Well, remember, carbons are donating, and donating decreases acidity. So meaning this one will lower the acidity compared to this. And therefore, this is lower in acidity. This is the most acidic of the three. So as you see, it's kind of an interplay between different factors, but with enough practice, you can analyze them properly and then rank them according to increasing or decreasing stability. Also, one last note is that sometimes you may be asked to arrange by basicity. And just remember that basicity is very much the opposite of acidity. So if you're gonna rank, for example, these three again in terms of basicity, you just have to invert the numbers. So the one which was number one a while ago would be the third in basicity. The one which is last a while ago in acidity is the first in basicity. The one in the middle will stay in the middle. And just like here, in terms of basicity, the one which is last in acidity is the most basic. The most acidic is the least basic, and the one in the middle is still in the middle. I mean, it depends on the scenario that you have for your test questions. But um, hopefully, I gave you some short examples because let me repeat what I said in IMFs. When I discuss IMFs, I discuss it in like 3 hours. I discuss it in less than 20 minutes. And here, I think I just exceeded 20 minutes when in fact I discussed these in like 3 to 4 hours normally. So of course, it's bound to have a lot of simplifications and omissions of special cases. If just so happens that one of your questions are part of those, feel free to ask because I might be able to answer them. But for now, this is the end of my simplified discussion on different structural effects, including strains, delocalizations, and inductive effects.